AP Chemistry students, we're going to be talking about collection of gas over water for tonight's lecture. And what we have here is we have a little lab setup, and so we'll kind of walk you through this. What we have is some potassium chlorate, KClO3, which is in solid form at the bottom of a test tube. We've attached to this test tube a stopper there, and we've got some tubing. Tubing is going to run into a little trough of water. What we've done is we filled up this container all the way full with water and then inverted it into the water. One end of this container is open right there, and we've got our tube in there. So we start heating our KClO3 up, and what's going to do is it's going to start decomposing. Down here we have a reaction. It's going to decompose into oxygen gas plus KCl, potassium chloride. And so the oxygen gas is going to be pushed down through this tube, and it'll start bubbling up in here. As it bubbles up in here and the oxygen gas starts to build up, it's going to push the water out and basically displace the water. Once the reaction's over, we could measure how much oxygen gas is left over at the end, and we could do that a couple different ways. So a lot of times in this type of reaction, and just not shown in this picture, we'll have increments on the side of these containers so you can tell how much of the oxygen gas is produced and how much of the water has been displaced. So let's look at a problem that involves this type of setup for a lab setup. So kind of scroll down here on this problem, and we have an example. A sample of solid potassium chloride is heated and decomposed. We gave us a balanced equation. The oxygen produced is collected by displacement at 22 degrees Celsius. The pressure, total pressure, is 754 torr. We have 0.650 liters or 650 milliliters collected of oxygen. Vapor pressure of the water at 22 degrees Celsius is 21 torr. That's going to come into play here in a minute. The reason why they're giving us that vapor pressure is as these oxygen bubbles travel up through the water, they're going to start picking up some water vapor. And you're also going to have water vapor bouncing around up inside here. So it's not just pure oxygen. You also have some H2O in a gaseous form up there. And that is contributing to a partial pressure. So you really do have oxygen gas plus you have the water vapor up there contributing to the overall pressure inside of that container. Okay, we're being asked to calculate the partial pressure of the O2 and the mass of the KClO that was used. So first thing we're going to do is we're going to use Dalton's law of partial pressures to calculate the partial pressure of just the O2 gas. Remember, Dalton's law says the P total in a container is equal to the pressure of the partial pressures of each gas present. So we're going to have the pressure of oxygen plus we're going to have the pressure of water. Now we're given two of these three. We're given our partial, or we're given the total pressure of 754 torr. We're also given the partial pressure of the water at this temperature, which is 21 torr. Now if you ever need to look for a partial pressure of water at different temperatures, they're given in the back of your book in the appendix. And so we'll look some of those up tomorrow. So we're asked for the pressure of the O2, so it just becomes a real simple 754 minus 21 equals the pressure of the oxygen. So we subtract those two and we get 733 torr. And that's our pressure, partial pressure of our oxygen. First step done. Okay, step number 2 is we want to find the number of moles of O2, because essentially they're asking us for the mass of the KCl. So this is going to be a stoichiometry problem. Now if we convert to moles, then we can plug it into and do our stoichiometry problem. So we're going to do PV equals nRT, because we know the pressure of the oxygen, the volume of the oxygen, we know R, and we know the temperature. So we're going to have N is equal to PV divided by RT. Oops, that should be a T right there. And so I'll put it down here. N is equal to, let me scroll down a little bit. Okay, so Okay, so N is going to be equal to the pressure, and we're going to use the pressure of the oxygen, which is 733 torr. And now I'm going to do a quick conversion. I want to convert that to ATM because we are using R here. Do that. We're going to multiply that by the volume, which was given at 0.650 liters. And then we're going to divide all that by 0.0821 liters atmosphere mole Kelvin multiplied by our temperature, and our temperature in this case was 295 Kelvin, and I just converted our given temperature in Celsius to Kelvin by adding 273. Okay, just double checking units, torr, liters, atmosphere, Kelvin. So we're left with an answer in moles, and that's what we're after. We run this through 2.59 times 10 to the -2nd mole of oxygen is being produced after we decomposed all of that potassium chlorate. Now, so we found that. Our third step here is going to be, we want to do stoichiometry to calculate grams of KClO3, potassium chlorate, and that's what we were after. So the stoich from our balanced equation is going to be 2 KClO3 decomposed into 3 oxygen molecules plus 2 potassium chloride molecules or moles. And so now that we know we have 2.59 times 10 to the -2nd moles of oxygen, we can just do some stoichiometry to get us to grams, ultimately grams of KClO3, potassium chlorate. So I'm going to do, from the balanced equation, I've got 3 moles of oxygen to 2 moles of potassium chlorate. Then I'm going to do my mole ratio of 1 mole KClO3. Sorry, this is not a mole ratio. It's just a conversion from moles to grams. And then I just calculate the molar mass of KClO3, which is 122.6 grams. And I'm going to run it through my calculator, and I get an answer of 2.12 grams of KClO3 used. So in this problem, we applied actually 3 different principles. We applied the principle of Dalton's law of partial pressures because there was a little bit of water vapor in that gas that was collected over water. We applied the ideal gas law formula, PV equals nRT. Then we did some stoichiometry. So this would be a good example of what we might see on the AP test, some problems like this where they ask you to do multiple steps. Tomorrow in class we'll do more practice problems.